thank Pablos and Mael for organizing this. So I really appreciate atomic orbitals, and you bring them together, and you have the symmetric and antisymmetric combinations of the atomic orbitals. They are called the bonding and the antibonding states. You put two electrons in the bonding orbital, and this is a way you form a hydrogen bond for molecular hydrogen. Okay, so if you understand that, the linear algebra that emerges in to understand the eigenstates of hybrid light matter system is very analogous. So if you think about, say, a single molecule inside of an optical microcavity that is highly reflective, so once in a while a photon will tunnel into the cavity, it will excite the molecule, of these individual excitations, right? So these are the upper and lower polaritons. Okay, so this G sub S, this individual light matter coupling, is normally very small, except in the case of, say, plasmonic nanojunctions, like those fabricated in the Baumberg group in Cambridge, or say, I believe that the first person who demonstrated this at room temp is the group of Gilad Haran and Weissman. So with quantum dots. So here they see Rabi splittings of about, say, 0.5 electron volts. And apparently this is robust, and this is happening at room temperature. The lines are broad, but then the Rabi splitting is even bigger. However, now I want to switch gears, and instead of talking hydrogen molecule, I want to talk about hydrogen fluoride. So this is a very typical problem that we give our students in the chemistry, in first year chemistry, where we say, okay, suppose you have a hydrogen atom and it mixes with the fluorine atom orbitals. Okay, so what happens is that one s orbital chooses its right partner to mix with, forming sigma and sigma star states, the bonding and the antibonding states, and it chooses the orbital PZ. And the reason why it does that is because of symmetry, right? The PZ orbital is aligned to constructively interfere with the 1s orbital. However, the 2px and 2py states, they have no real overlap with the 1s orbital, and therefore they remain parked at the same energy and as the original atomic orbital. So they are out of the party. They remain left out of the party. And they are called the non-bonding states. Okay, so if you understand this analogy, then the following spectrum should make sense. So if you dump, say, 10 to the 6 or 10 to the 10 molecules inside of an optical microcavity, like the experiments that you guys routinely do in your research group, then the density of states is such that you have one photon mode per, say, 10 to the 6 to 10 to the 10 molecular modes. So because there are many molecules fitting inside of a micro instead of a nano cavity. In that case, there's something very nice that happens, which is a super radiant phenomenon, whereby the lower and upper polaritons are now split by a giant Rabi splitting that scales as square root of n, where n is the number of molecules. This Rabi splitting it must be emphasized that it's collective. So despite G sub S being really small, this individual light matter coupling being very small, collectively they do way better, showing this drastic change of energies. But make no mistake, because most of the most of the states that of the spectrum, most of the excitations in the spectrum remain part of the same energy as the original molecular transitions. They are they are completely analogous to the non-bonding states, and they are called in your literature the dark states. So if there are n molecular transitions with mixing with a photon mode, there are 2 polaritons and n-1 dark states. So if n is 10 to the 10, then there is pretty much 10 to the 10 minus 1 dark states, right? Pretty much 10 to the 10. Okay, so that's the price to pay, right? So these things don't have the right symmetry to mix with a photon and remain purely molecular. So with disorder and with vibronic coupling, there are some subtleties about that, and I will talk more about that in a moment. These are some experiments that my colleague Wei Xiong has carried out in UC San Diego, where he's focusing on vibration. So he deposits microfluidic solutions inside of these optical microcavities, and he demonstrates vibrational strong coupling between, say, localized molecular vibrations in tungsten hexacarbonyl at 1983 wave numbers, coupled to a cavity mode forming the polariton states. And again, this is the linear transmission, and it's both literal as well as a figurative optical illusion that you don't see the dark states. The reason why you don't see them is because they don't have the photonic component to show up in the linear transmission spectrum. But again, they are there, and they are entropically, they make most of the states in the system. And if you look at, say, nonlinear optics, you will see them. Or if you think about chemistry, the reason why I'm emphasizing them is because in chemistry, they matter, and they matter a lot. Okay. Now, my colleague, Vinod Menon, so he puts these molecules inside of optical cavities. So these are molecules that undergo excited state proton transfer, HMPP, and they see huge Rabi splittings when they put the molecules inside of the optical cavities of 1 electron volts. Okay, I apologize. Okay, so now 1 electron volts is a sizable fraction of the optical gap, in which case, sorry.
Joel, bless you.
Thank you.
Bless you. And we have one question that has come up, and I'm inclined to take it. So, Anton.
Yes, thanks a lot. Can I ask here, what defines the polariton line width here? Is it the cavity lifetime or the dephasing of vibrons? What's actually?
Yeah, so in this case, so they always choose the cavity to have low quality factors because the molecules have very broad line width. So I think here they were not interested in condensation or anything like that. So they were just matching the line widths pretty much. So both contribute.
Okay, but what is the typical dephasing time for vibrons?
Okay, so I think you guys have this very strange term for chemists, which you call them vibrons. Okay, so let me say a few things. So for vibrational modes in the ground state, I would say is just this is like 10 wave numbers. So I would say that's 10 wave numbers is 10 wave numbers. I think is what 1 MeV, maybe. I think that's approximately it. But then obviously for UV visible transitions, that's just like the molecules you guys use for your polariton-condensate experiments. These are really broad transitions because in principle there are many vibronic states here, right? So they just choose like a cavity that encompasses pretty much the entire band, the absorption band. Or something like that. Does that make sense? Does that make sense, or was that?
Yeah, sure. No, that was exactly my question. Actually, what dominates in the losses for polaritons in terms of when you couple not the electron transition, but instead some vibrational.
Yeah, so vibrational transitions in the ground state are much the line widths are much smaller because you're really addressing a single molecular vibration. So so people think about tungsten hexacarbonyl as the hydrogen atom for infrared spectroscopy because everything that people try with infrared spectroscopy, they first tried with WCO6. So that's what they use because the spectroscopy is very, very well characterized. Yeah, thank you. Okay, so this is a sizable fraction of the optical gap, and we're in the ultra strong coupling regime. So this is a review that was written not by me, by others in the community of the different versions of light matter coupling. So weak strong, ultra strong, and deep strong light matter coupling that most of you are familiar with. So a few years ago, I went to my local supermarket and I noticed that people in the consumer product industry, they also like these words, just like the Polaritonics community. But I put a trigger warning, so no one wants to consume, you know, the perturbative regime anymore. The ultra soft, they all want ultra strong. I put a trigger warning because I used to give this talk in March 2020 and all the aisles were empty, right? So then this would make people very upset. Anyway, so why do we care about molecular polaritons? Well, okay, so you can create devices, and a lot of you in your group have showed like transistors and switches, and you can work on condensates. And again, you guys are also like some of the leaders in this field. And I got interested in this problem mostly from the chemistry point of view, but as I will show you, I believe that there should be a very interesting connection between the condensation research and the chemistry research. So if you're interested in this subject, from the chemistry point of view, I recommend you this review that we wrote. And let me just show you very quick snippets that I tried to choose so that they would connect closely to what you guys are familiar with and maybe entice some of your interest in this subject. Okay, so since most of you don't work on vibrational polaritons, I want to show you the similarities and differences that exist with, say, organics or with solid state systems. So this is work done by my colleague Wei Xiong, Bo Xiang, and a postdoc in my group that now is a professor in Emory, and in the Naval Research Group in the US, Adam Dunkelberger, Jeff Orotsky, and Blake Simmons. So what they did was that they first put tungsten hexacarbonyl inside of an infrared optical cavity. They saw the upper and lower polaritons, and they took the transient absorption, but they were not fully understanding what was going on. So then they went to my colleague who works on 2D spectroscopy. And my colleague took the first 2D spectrum of this type of systems. And they were very puzzled about these things that look like derivative line shapes. So normally in molecular systems, these things don't show up like this. So what we did was we combined the input-output theory from quantum optics with the theory of anharmonic vibrations in condensed phases developed for 2D IR. And what was important to model this spectra was to say, okay, the photon is a harmonic oscillator. The molecules are anharmonic, where this delta is so-called mechanical anharmonicity, which means that in the vibrational ladder, the higher that you go up in the vibrational ladder, say the smaller and smaller the optical transitions become. So like a Morse oscillator. And the light matter coupling also has so-called electrical anharmonicity, where you go upper and upper in the vibrational ladder, the vibrational transitions become weaker and weaker or stronger and stronger. Okay, so here are the timescales that we need to think about in these systems. So because there's a large density of dark states, and there is even more in infrared systems than in UV visible system, there is a very large entropic drive to go to the dark states, according to Fermi's golden rule that tells you the larger the final density of states, the faster the rate. So this happens around in the order of 10 picoseconds or so. Now, what's really puzzling is that once you trap population in the dark states, it seems that it doesn't leak out, and this is because, again, the density of states of polaritons is very small compared to the dark states. Okay, so transitions into the dark states are very, very fast, ultra-fast timescales, similar to molecular ultra-fast timescales. Transitions out of the dark states are very slow, unless you have situations like condensation that I will describe later. Okay, so here is what my colleagues saw. So suppose at the beginning, just out of just for purposes of illustration, you have, say, 5 molecules. So then you have a Rabi splitting that is proportional to square root of 5 between the upper and lower polariton. So forget about this right-hand side. Now you pump, say, the upper polariton, and then there's quick relaxation of that population into the dark states of, say, the fundamental transition of the molecule, right, to the 0 to 1 transition. So there is dark state population. So now instead of having instead of having 5 molecules, you have only 3 bright transitions. So the Rabi splitting becomes square root of 3. So there's an optical saturation of the transition. So in that case now, but you also have the ability to go from the first fundamental transition to the doubly excited state. So now, instead of just having saturation, which is the Rabi splitting contraction, you also have mixing with this anharmonic transition. And that's what you see in the experiment. You see these 3 peaks in blue, 1, 2, and 3. And without pump, you only see 2 transitions, which are the upper and lower polaritons in the absence of Rabi splitting. So then there is larger Rabi splitting. Sorry, in the absence of Rabi splitting contraction. So in that case, now when you subtract the blue minus the red, you have 5 peaks. And this is exactly what you see in the experiment, right? So this is what we see in experiment. This is drastically different ultrafast transmission for a system that is outside of the cavity. So this is purely molecular. This is the polaritonic system. So the first summary is that, okay, the Rabi splitting contraction is due to mechanical and electrical anharmonicity. So these saturation effects are the ones that dominate the nonlinear optical spectrum at long times for these systems. And there are other curious features in these systems that I don't want to discuss much, because I think they are quite complex, but this is what matters for the rest of the talk. Okay, so we said we have this possibility of changing energy levels in an ultra-fast timescale. Can we do something like a device, like a chemical device? And the answer is, so that's what we wanted to propose. So actually, I didn't even know that this was also work by your group. So okay, so Litzy and you guys, you had this experiment where you showed that there's energy transfer between dyes that normally don't transfer energy between themselves inside of the cavity. And later on, so actually, I think the first paper that I saw when I was a postdoc on polaritonics was this one, actually. So this one, I started thinking about polaritons kind of like with this paper. So later on, the Evison group, they did the same experiment, but then they separated donors and acceptors, say across, say, hundreds of nanometers, and they demonstrated that energy transfer happens even when the chromophores are far apart, even when the Fred radii is much smaller than the separation between the molecules. So the way we explain this in this paper is that if you have, say, if you excite the upper polariton, then you say statistically decay into the dark states and the of the donors and of the acceptors. Okay, so there's a Hopfield coefficient, and then the population into the dark reservoirs is statistically distributed. So then that's not interesting, but what's interesting is what happens afterwards, that after a while, after this statistical decay, there is funneling of population apparently passing through the middle polariton. Okay, so the middle polariton is kind of the bridge that takes energy from between this reservoir and this reservoir, because it has character of both of them. So we used to find it puzzling that energy transfer can happen in this type of systems, because if entropically, it's very unlikely from a vibrational relaxation point of view, because again, because of Fermi's golden rule, as I described. But now that we understand that this process is mostly due to so-called radiative pumping that you guys know well, and I think in that case there is no, I think there is not as much mystery. But still, I think it's quite interesting that you can really do this energy transfer, right? Now, what my colleague did was reproduce the same idea, but with vibrational chromophores. What I think is very interesting in this case is that vibrational chromophores never transfer energy between themselves. So what he put 2 isotopomers of tungsten hexacarbonyl, and then he parked the cavity at the middle between those two isotopomers. And what he saw was that there, in 2D spectroscopy, he saw that within 10 picoseconds, there was transfer of energy between one isotopomer and the other. And that never happens outside of the cavity, because the dipole-dipole interactions in that regime are very weak, and they are screened by solvent. So this demonstrates that the cavity really affects the chemical dynamics of these systems, and this is beyond the statistical decay. Now, I will explain to you later why this is puzzling, and we believe that we have a explanation of this puzzle, because in principle, if you just plug in numbers of like how many states you have in the dark manifolds compared to how many states you have in the polariton manifold, you shouldn't be able to see this process. Like, and these molecules don't have Stokes shifts, right? Like Stokes shifts don't happen, are not substantial in the vibrational regime. So something else different from your experiments is happening in these infrared systems. Anyway, the question was, if we can do remote energy transfer, say across say microns, according to these calculations, can we do remote control of chemistry? So this is the idea. Suppose I have these catalysts that you need to excite, and then the reactants are on another vessel. In which case, if I excite the catalyst and I excite the product, I excite the reactant, then I can see the product, but otherwise I don't see the product. So this was our idea. So this is a paper in Chem, and the idea is, say, let's take some left cavity and let's put some remote catalysts, and if you excite the molecule, there is no isomerization. But then if you pre-excite the left cavity, there is isomerization. Okay, so we go to 1960s physical chemistry, and people notice that there are these chromophores that if you photoexcite the OH stretch, it induces a very slow torsional isomerization that converts the molecule from cis to trans. So this happens within 10 picoseconds. Okay, so there is a branching ratio between cis and trans. So there's coupling between this degree of freedom and this torsional degree of freedom. So I told you that in an ultra-fast time scale, because of the saturation of the vibrational transitions, because of the anharmonicity, you can do Rabi splitting contraction in a very fast time scale, right? So in an ultra-fast time scale, you change the optical spectrum of these systems. So why don't we use this for something practical, right? So we say, okay, we have a left cavity and it has some remote catalysts that labeled by R, and they form the polaritons and they have their dark states. We have the right cavity with the vibrational chromophore and the torsional transition. We have their polaritons, they are coupled to their cavities. And then in the presence of coupling between the cavities, this is the spectrum you have. You have 4 different polaritons in that case. So if you photoexcite, say, here, because there is no resonance, the polaritons are not resonant at the energy, there is little overlap between the transition that induces the photoisomerization. So then you see no reaction. But now what if you, say, photoexcite the uppermost polariton? then by entropy, you will have a statistical decay into the dark states, mostly the dark states on the left-hand side. So then what that means is that you have localized energy on the left cavity. That shrinks the Rabi splitting in the left cavity. And because everything is coupled, now you align the resonances so that if you park your laser at the same energy, now you will have a reaction. So this is like a switch, right? So a switch that depends on optical saturation. So you can show that depending on the amount of pump that you have, the amount of saturation, you can change the yield of the reaction by orders of magnitude. And something pretty that you notice is that if there is no communication between the cavities, if there is no coupling, no matter how you pump the system, you will see no changes in the yield, right? So this is the relative yield. But as soon as you open the communication between the cavities, you see changes in the yield, right? So which shows that really this is a remote control process. And clearly there's a very trivial way to also control this process if you don't even have ultra fast lasers, right? You just keep changing the concentration of the catalyst, and that changes the energy level. So this will be in a very slow human time scale, but you would still be able to see this remote control. Okay, so this is what we wanted to show, that you can use this nonlinear optical switching of the polaritons, which I'm sure you guys have also thought about similar things, but we wanted to really exploit this advantage of the remoteness of the possibility of communicating molecules to do something interesting like remote chemical reaction. Okay, so now I'm going to tell you now things that do not work. Okay, so and I think this is important because this is related to a lot of the things that you guys show that do work. So I would like to use this to start some conversation about this. Sorry, give me a second. I realized I deleted this. I deleted this. Give me a second. I just want to open the actual file. Give me a second. And in the meantime, if you have any questions, please feel free to ask me.
Yeah, while we're waiting for the file, maybe you can tell us how fast is the switch, and does it depend on the lifetime of the molecules that you're saturating, or you can accelerate somehow the lifetime?
Yeah, so how fast is the switch depends on the population of the dark state manifold, right? So in that case, it's about 10 picoseconds. So that's the population of the relaxation to the dark state manifold. Yeah. Okay, so let me show you a problem that we worked together with Stefan Kenna-Cohen in École Polytechnique. So this concerns the following problem of, so Stefan had this idea, and there are other people in the field that had this idea, that say you inject electrons and holes inside of organic polymer, and you want the excitons that are formed to emit light, so to serve as an LED, organic LED. The problem about this process is that often it's a little bit inefficient because there are, most of the excitons that are formed are triplet excitons. So 75% by spin statistics is triplet excitons that don't emit light. In which case, say, so they are these red parabolas, in which case the population that is formed in these triplet excitons just at long time scales, it just ends up being heat, unless there is a transfer into the singlet state, in which case they radiate light. Okay, so a big problem of this field is the low efficiency due to formation of triplet excitons, low efficiency of electrical to photonic conversion due to the triplet excitons. So the question was, if you put a lower energy state, lower than the triplet, so normally the singlet is above and the triplet is below. So then we wanted to put a energy state, a polariton energy state that would be lower in energy than the triplet, to see if that state would harvest the energy before it gets lost into heat. Okay, so it looks like a very interesting idea, and we plugged in numbers. We constructed a vibronic model for that. And this is a funny problem because it involves electrons, photons, and phonons. So it's not that easy. So it's like a special type of spin boson problem that many people are studying nowadays. And we use these things called the vibrational polaron transformations that I will skip. But the point is that you do a canonical transformation to partition your system into, say, a zeroth order Hamiltonian and some small perturbation that you can actually use perturbation theory and write a master equation. Okay, so that's kind of roughly the idea. And there are many regimes of reactivity that you can see. But then the important thing is that in the experiment, my colleague Stefan saw no changes in the delayed fluorescence of this dye that was a so-called TADF dye. It's called thermally activated delayed fluorescence dye. Okay, and the reason is very simple. It's just that when you plug in numbers and you say, what is the rate going from triplet to lower polariton branch? The rate is 10 seconds to the -1, which is an absurdly small number. And the reason is because you can see it here. The efficiency of this process becomes smaller and smaller the larger and larger the number of molecules there are in the microcavity. And this argument can be understood rather easily. So sure, you can change the energy level of the polariton at will if you wish, and that changes the activation energy, which plays an important role in reactivity. However, there is always this entropic penalty of 1/n. 1/n because the triplet state is a localized state, whereas the polariton state is a delocalized state. So the probability of the localized state seeing its partner in the delocalized state is 1/n because the delocalized state is distributed across n molecules. So another way to say this is that because reactions are local and polaritons are delocalized, transferring into a polariton state is normally a very slow process and it shouldn't be happening. Okay. Now, then a colleague of mine in Cornell University, Andrew Moser, did a similar experiment, but with a different dye, with different type of photophysics. And it turns out that in that case, they were doing triplet annihilation. In that case, they did see an enhanced photoluminescence at long times. And we did a simple model for them. And what we realized is that despite the rate going from this dark manifold to the lower polariton branch directly being extremely slow, 20 microseconds, so it's a bit faster than the previous one, because the kinetics, because the population is trapped so efficiently in this process, because there's a very fast rate of conversion of singlet to triplet. So going back from triplet back to singlet is really difficult. This is just like a fast equilibrium effect. So it's a Le Chatelier's principle effect. And once you have population trapped in this manifold, it becomes really hard for it to first go to the singlet and then jump into the lower polariton. So it directly goes to the lower polariton, and it contributes to the delayed photoluminescence. So it's not that it makes the chemistry much better. It's just that like the rate was so bad at the beginning that anything that you put in was already better than what you had before. So it turns out that polaritons, in my opinion, in these photophysical processes, they are very unlikely to change photophysics if you already had a very efficient material that, like this TADF material. But then if you had something that was very, very, very slow, chances are that like poking a small hole in the sink will will make the reaction, or in this case, the photophysical process a little bit faster. So the summary is that not because you put the energy level lower than the dark reservoir, you should expect transfer of energy into there, because vibrational relaxation is very slow. Now, there are other processes that depend on radiative pumping, and those, in my opinion, are different, and they should work under many circumstances because they don't rely on these 1/n factors. They only rely on emission of light from the Stokes-shifted molecule into the polariton state. Okay, so in the last part of my talk, I will discuss the processes of condensation. Okay, so let me just go back to my original presentation. So all of you guys are interested in condensates, but and we saw this paper that we thought was really cool about how you can stimulate the scattering from bands that normally are, well, how you can use stimulated scattering to induce processes that normally don't happen. And we were thinking, okay, so what's cool about condensates is that they are not just lasers, right? Like there is the matter part, and in principle, and we're chemists and we're interested in how to affect the matter component of things. And at the beginning, we were saying, okay, maybe we should use stimulated scattering to catalyze certain reactions, but things are not. But there are some reactions are not as fast. So so we decided to take a different approach. So so looking at the work that you guys had done, we were thinking, okay, so let's start easy from a theoretical point of view, and let's just talk about pure vibrations, because vibronic systems are not that easy to think about as a first step. So purely vibrational systems in the electronic ground state are much easier to think. However, no one has shown vibrational polariton condensation. Okay, so, but then we plugged in numbers, right? So we said, what would it take to be able to see a lower polariton condensate of, say water molecule infrared transitions in a cavity? So what we show, and this is easy to understand, is that it's not that the Rabi splitting needs to be very large, right? Is that the separation between the dark state and the lower polariton needs to be very large. Okay, and that gives you a little bit more parameter space to play with, and the mathematical condition that you need is that the Rabi splitting minus the light matter detuning needs to be larger than KBT. So what we see is that if you make a plot of, say, this is a plot of the amount of excitation that you need to dump per molecule. So if you look at, for example, say this lower region, which is a 0.1 excitations per molecule, you can see that if the detuning is negative, so the lower polariton is more photon-like, then you can achieve, in principle, polariton condensation with vibrational strong coupling, right? So in this region where the Rabi splitting is moderate, but then the lower polariton is also more photon-like. And we see that, say, for example, for water, people have seen huge Rabi splittings. And this is not surprising because water is by definition very concentrated at 55.5 mole per liter. So no wonder why you have this huge Rabi split. Okay, now I explained vibrational polaritons. I want to find a situation where vibrational excitations really matter for reactivity. So let me go back to a Nobel Prize winning theory in chemistry, which is called Marcus electron transfer theory. So in the 50s, Marcus noticed the following. So chemists used to think the lower and lower the energy of the free energy of the product is, the faster and faster the reaction should become. But Marcus told them that that's not true because kinetics is not the same as thermodynamics. And you know, what's important is not that the energy of P is low, but what's important is the intersection between the reactant and the product is not very high. So here there's a high energy barrier. Then as you lower the energy of the product, there is no energy barrier. And then as you lower the product even more, there is high energy barrier. So then what Marcus said was, as you lower and lower the energy of the product, the rate should first go up and then it should go down. And no one believed him. And in 1984, Claus did this experiment that exactly showed what he predicted. First acceleration of the reaction with increasing minus delta G, and then deceleration. This part is called the inverted regime, Marcus inverted regime, because the lower and lower, the more thermodynamically stable you make the product, the slower you make the reaction. So that's the physically interesting part of the Marcus curve. But then Jorner in '76, what he noticed was, okay, you know, molecules are kind of complicated beasts. So you have this reaction coordinate, which is like some slow solvent reaction coordinate that like aligns its dipole for the electron transfer to happen. But then the molecule also has its own high frequency vibrational modes. So for example, a CO stretch. So suppose there's a huge energy barrier to overcome. So going from reactant to product. Well, Jorner said, you know, the parabola can be shifted up if you, there are high frequency modes that give you additional states, so that instead of going this way, you can go this way and you can afford a lower energy barrier, in which case you create one high frequency mode excitation, for example, a CO excitation, but then you catalyze the reaction. In other words, at the expense of dumping one quanta of high frequency mode of excitation into the high frequency mode, you can catalyze the reaction and going here, and then there's very fast decay from here to here, right? So the summary is you could go here or here, but then there's lower energy barrier here, so you go this way, but then you have accumulated one quanta of, like, say, a CO stretch. But then there's a very fast relaxation of that CO stretch, and then you decay. So he says, instead of doing Marcus inverted regime, you could always go through this other path. But this is exactly what we wanted. We wanted a situation where vibrational excitations really matter for chemistry, which is in this case. So the high frequency mode catalyzes the reaction. So my students in Nana did the following calculation, which I thought was quite interesting. So she took, say, a donor acceptor of electron system, and then she said, first, I want to understand what is the difference between catalyzing a reaction with an infrared laser and catalyzing a reaction with a vibrational condensate, right? So in the first one, the coherence is outside. In the second one, the coherence is inside. Okay, so if the coherence is outside, if you just drive the molecules with a laser, what you're really doing is, say, shifting the free energy of the reactant. Namely, you're dumping additional free energy into the reactant, so that in this case, you need to have, when you go from reactant to product, you create one excitation in the high frequency mode. You cannot create one de-excitation because you started in the ground state. But when you put laser energy, you create like a replica of parabolas, say, where you can dump where the vibrational excitation can be, one vibrational excitation can be lost or can be gained. So then you create like a replica of different parabolas that can cross this reactant potential energy surface shown in yellow. So if you look at, say, the yield, the yield plot, you will see some very interesting features. For example, you establish some steady state, and you see that you would even have yield for positive delta G, where normally, if the reaction delta G is positive, then without laser excitation, you should have no yield. You have 0 yield. But because you have photons now, and you say you dump about 0.1 photons per molecule in the cavity, sorry, outside of the cavity, then you see some probability of having the reaction even when the reaction was not spontaneous outside of the cavity. And you also have some interesting features, like, for example, you can suppress the reaction completely when the reaction was spontaneous, right? So this is an effect of canceling the forward and backward rates. Okay, but then the important thing is that for this type of control, you can only make the parabolic, the potentials shift by 1 quanta of vibrational excitation. But when you have the condensate, you have a lot more pathways. And why is that? Is because, for example, if you start with a condensate of say, many excitations in the lower polariton, then you can redistribute that energy when you go from reactant to product into, say, n-1 lower polaritons and 1 dark state, n-2 polaritons and 2 dark states. And actually, the separation of energies between these different parabolas is not 1 quanta of vibrational excitation, but it's a Rabi splitting. So the Rabi splitting is much smaller. So then you basically get a continua of tuning the separation of energies between the different polaritonic energy surfaces. And what that does is that you can always find situations where you can cancel the activation energy, right? Like this crossing means that going from the yellow to the red gives you almost no activation energy barrier. And that's why you get like a much larger, much richer control of the yields of the reaction. And there's a lot of physics that I should skip through here, but the point is that the condensate provides essentially a quasi-continuum of reactive channels separated by Rabi splitting rather than by vibrational excitation. And then you can have yields that are more malleable even when delta G outside of the cavity was very positive.
Joel,
So this
before
is
you move on, sorry, Joel, before you move on, Anton has a question at this point.
Yes.
Yeah, thanks. Can you please elaborate a little bit in details why the manifold appears? I didn't get. So is it just because you are talking about different amount of, let's say, molecules involved into the polariton state, something like that? Or?
No. So let me first clarify. So
okay. I mean, I'm talking about the manifolds on the next slide, by the way. Okay, just.
Yeah. So
yeah.
So for example, like, do you agree that if you have, say, the difference in energy between n-1 n lower polaritons and n-1 lower polaritons and 1 dark state is approximately half a Rabi splitting?
Okay, it's just because you have less amount of states available for the strong happening, right?
More than that, it's just because the separation of energy between the dark state and the lower polariton is half Rabi splitting. So,
okay.
So in that case, okay, so suppose I say I am going to put 5 excitations, and what I have is lower polariton, upper polariton, and dark modes. Okay, so can you see that, like, say, those 5 excitations will be separated in energy by, say, half Rabi splitting. So each of them is going to be separated by half Rabi splitting because, say, if I have 5 lower polaritons, that has energy 5 omega lower polariton. If I have 4 lower polaritons and 1 dark states, you will have the same energy but plus half a Rabi splitting. So then
right. Sounds right. Yeah.
So essentially you get basically very fine tuning of the energy levels because you have now new vibrational modes. That's the way you should think about it. Like in the previous case, you were stuck with 1 vibrational mode of the molecule. Now you have, or of the laser, right? You only had like 1 quanta. But now, because you have more modes, now you have more malleability of the frequencies. So now you can have better redistribution of energy among all the modes. and then now you can cancel the activation energy very efficiently. So this is chemistry with laser excitation and polariton condensation is very different, right? So, and even just from a very naive natural question, like you could ask, okay, chemistry has been tried with lasers. What is the analogous chemistry with polaritons? Like, it shouldn't be the same, right? Because in one case, you need to do two steps. First, laser goes to the reactant then goes to product. In this case, now the condensate reacts directly. So here, the summary is that the energy deposition among the modes is richer in the condensate than in the molecules. And I believe that there's a huge open field here of thinking about condensates and the chemistry afforded by the condensates. So, so that's that. So I showed you a bunch of snippets of the things we have been doing in this group. Some of them is work done in collaboration with experimentalists. Some of it is our own dreams, like this condensate chemistry that we're trying to actively persuade our colleagues to try. And so I just want to conclude by saying that we should think inside of the photon box, because, you know, in the past, say, Einstein and Bohr were thinking about photons in boxes, and Harosh and Wineland got the Nobel Prize for thinking about photons in boxes. They didn't know that they were, like, Einstein and Bohr would be very pleased to know that Harosh and Wineland were really bringing their Gedanken experiment into real life. And you know, okay, so the idea of using cavities for chemistry, I would say, is by Evison. And I think he said, you know, I don't think you can do quantum information processing super cleanly in these systems, but I would say that for materials and for device applications, I think there's a lot of interesting things, and especially for chemistry. So this is the review, and then so this is funding, and thank you for your attention, and I'll happy to take questions if there are any.